So I forgot to show the review slides, so let's look at the review slides. So we basically talked about two kinds of waves. A transverse wave, where the wave pulse is going this way, but the piece of string is going that way. So this is transverse to that, because transverse means perpendicular. So that's like your typical rope wave. Then we also talked about a longitudinal wave, where you have like a spring, and you don't do this, you do this. You know, you just back and forth, back and forth, back and forth. So the wave pulse goes that way, but the displacement goes in the same, well, it goes like this. All right? So here, perpendicular, here, parallel or anti-parallel. Definition, a wave is a self-propagating disturbance that travels through an elastic medium, transports energy and momentum. Wave speeds, I don't really care too much about this one, but this is important, right? String or thin wire. The speed only depends on the tension and the mass per unit length. And this we'll talk about in Physics 106. Everybody measures the speed of light to be the speed of light. Doesn't matter how quickly the source of the light is going. Doesn't mean how quickly the observer is going. Doesn't matter. Everybody measures speed of light to be the speed of light, which is crazy, but we'll talk about it. Then we talked about when you visualize a wave, you know, there's really two things going on, right? There's an x dependence of the displacement, and there's a time dependence for the displacement. So that's why we talked about snapshot graphs, where you're just looking at well, what's a snapshot? It's a photograph, right? At one particular time. So you're looking at the entire wave. So you're looking at the x dependence of the wave. Then the history, you know, history means over time. So for the history plot, you're looking at one specific piece of that wave, you know, for time and all eternity. Just kidding. And this is nice because it shows you that the displacement, you know, the hump, right, depends on position and time. So that's why we need the two plots to discuss it, because it depends on the displacement, depends on the position and the time. So snapshot, y versus x, because there's, you know, it's only one time. And so all you can get from that is a wavelength. History, you're looking at one piece of the rope or whatever over time. So it's y versus time. You can get period. That's all. And then we put them both together because we wanted the wave to travel. And here it is. A cosine 2 pi x over lambda minus t over tau, t over uppercase T. And again, you know, we're talking about sinusoidal waves, and they're periodic in wavelength and period. And you can see it right there, you know. All right. Oh, yeah, and one more thing. So look at, this is really awesome here. So we're looking at this right here, correct? And so this pulse, okay, so this is time equals 0. Here it is at lambda. So now it's a little bit to the right, a little bit to the right, a little bit, okay, a little bit to the right, here it is. So you notice it went from here to here. So it traveled one wavelength. And look at the time. How much time did it take to do that? Well, 0 to uppercase T, right? So that's what we mean by sinusoidal waves being periodic in wavelength and period. The pulse moves, this pulse moved to the right one wavelength in one period of time. There you go. This is the F equals ma of waves. It's always true. Velocity equals frequency times wavelength. For light, we just put a lowercase c here, because lowercase c is the speed of light. And from that last equation, c equals f lambda. So this is constant. So this can be, these two can be anything as long as the product equals c. So you have, you know, different kinds of light. You have high energy light, low energy light, high frequency, low frequency, long wavelength, short wavelength, all these different types of light. And again, visible light is only this little tiny region there. And so we talked about how important that was to astronomy, to figure out how to detect all these other types of light. For a point source, it doesn't have to be light, could be light, sound, radioactivity, whatever. For a point source, okay, intensity is always power over area. For a point source, you're looking at a sphere. So the area of the surface area of a sphere is 4 pi r squared. So the important thing is that the intensity is proportional to 1 over r squared. That's the important thing. Sound intensities, there's this crazy range, right? From 10 to the minus 12 all the way to 10 to the 1. And so how do you handle that with logarithms? So this is just something that people developed. Sound intensity, all right, these are intensities because it's watts per meter squared. But if you use logs, they call it sound intensity level. So beta 10 decibels times log of that fraction. And then we talked about Doppler effect. And again, these are the 4 formulas for sound. Make sure you know what the variables stand for. And then we had the Doppler shift on the reflection from a moving object. Again, if you're a police officer or if you're in a hospital measuring the speed of blood moving through an artery, you'd use that. And then this is what astronomers use to measure the speeds of galaxies moving towards or away. And then the last thing was a shock wave. A shock wave happens when the speed of the source, like the duck, moves greater than the speed of the water waves or any kind of wave. And that is it, I promise. Thank you.